Lieutenant Commander Hiroshi Nakamura squinted through his cockpit canopy at 25,000 feet, the absolute ceiling of his Mitsubishi A6M0. Above him, impossibly high, silver specks moved across the Pacific sky like distant stars in broad daylight. His radio crackled with panicked voices from fellow pilots reporting the same phenomenon. American bombers flying at altitudes that defied everything they knew about aviation. What Nakamura witnessed that September morning in 1944 would shatter Japanese air defense doctrine and introduce them to a technological marvel they never saw coming: the Boeing B-29 Superfortress, cruising effortlessly at 30,000 feet while Japanese fighters gasped for air thousands of feet below.
Before we jump back in, tell us where you're tuning in from. And if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The morning sun cast long shadows across Iwo Jima's volcanic landscape as Captain Robert Dutch Kellerman adjusted the oxygen flow to his mask and checked his altitude gauge one more time. 32,000 feet. The numbers seemed surreal even to him, a veteran pilot who had flown everything from crop dusters in Kansas to P-40 Warhawks over Burma. Yet here he was, piloting the most advanced bomber ever built, floating through the thin air like a steel leviathan in an ocean of blue. Kellerman's B-29, christened Prairie Thunder by his crew, was part of the 498th Bombardment Group's maiden mission over Japanese-held territory. The sleek silver giant measured 99 feet in length with a wingspan stretching 141 feet, dimensions that dwarfed every previous bomber design. But size wasn't what made the Superfortress revolutionary. It was what happened when those four massive Wright R3350 Cyclone engines pushed 2,200 horsepower each through the rarefied atmosphere above 6 miles high. Technical Sergeant William Kowalski, hunched over his flight engineers panel, monitored the complex systems that made this altitude possible. The cabin pressurization system maintained a comfortable environment equivalent to 8,000 feet, while the aircraft soared at stratospheric heights. Banks of instruments tracked oil temperatures, manifold pressures, and turbocharger operations with precision that would have seemed like science fiction just 5 years earlier. Every dial and gauge told the same story. They were operating in airspace no combat aircraft had ever sustained before. Below them, spread across hundreds of square miles of Pacific Ocean, the Japanese home islands appeared as brown smudges against azure water. At this altitude, the curvature of the Earth became visible, giving Kellerman and his 9-man crew a perspective reserved for gods and eagles. The strategic implications were staggering. Japanese fighters, bound by the limitations of their engines and airframes, simply could not reach them here. Staff Sergeant Michael O'Brien, manning the tail gun position, scanned the empty sky behind them through his plexiglass bubble. In previous wars, bomber formations flew at altitudes where enemy fighters could intercept them with relative ease. The flying fortresses over Europe operated between 20,000 and 25,000 feet, well within range of Messerschmitt Bf-109s and Focke-Wulf 190s. But the B-29 had rewritten the rules of aerial warfare by climbing into a realm where oxygen masks became critical and where conventional piston engines struggled to produce sufficient power. The technology packed into Prairie Thunder represented America's industrial might concentrated into a single airframe. The remotely controlled gun turrets, operated by gunners using advanced computing sites, eliminated the need for multiple crew members to physically man defensive positions. The Norden bomb sight, coupled with radar navigation systems, allowed unprecedented accuracy from altitudes that rendered ground-based anti-aircraft fire virtually useless. Lieutenant James Tex Morrison, the bombardier, peered through his equipment at the target below, an aircraft manufacturing facility on Honshu that appeared no larger than a postage stamp from their lofty perch. The mathematical calculations required to drop ordnance accurately from such heights pushed the boundaries of ballistic science. Wind drift, air density, temperature variations, and the Coriolis effect all factored into computations that would determine whether their missions succeeded or failed. As Prairie Thunder maintained its steady course, radio chatter from Japanese fighter pilots filled the airwaves on frequencies the Americans monitored. The voices, translated later by intelligence officers, revealed confusion, frustration, and disbelief. Pilots reported climbing to their maximum operational ceiling of 25,000 feet, only to watch helplessly as the American bombers passed overhead with thousands of feet to spare. Captain Kellerman reflected on the journey that brought him to this moment. The B-29 program had consumed resources and engineering talent on a scale comparable to the Manhattan Project. Boeing's factories in Wichita, Kansas and Renton, Washington worked around the clock to produce these technological marvels. Each aircraft cost approximately $640,000, more than 3 times the price of a B-17 Flying Fortress and equivalent to millions in today's currency. The development process had been fraught with challenges that nearly derailed the entire program. Engine fires, pressurization failures, and structural weaknesses plagued early test flights. General Henry Hap Arnold, commanding general of the Army Air Forces, had staked his reputation on the Superfortress program, pushing for deployment even as engineers worked frantically to resolve persistent problems. Now, cruising serenely above the Japanese mainland, those investments and sacrifices were paying dividends. The B-29's 4-engine configuration, advanced aerodynamics, and pressurized crew compartments had created a bomber that could strike targets while remaining virtually immune to interception. The psychological impact on enemy pilots, watching helplessly from below as formations of silver giants passed overhead, was immeasurable. Technical Sergeant Kowalski's instruments registered the efficiency of the turbo-supercharged engines at altitude. Unlike naturally aspirated engines that lost power as air density decreased, the B-29's power plants maintained performance by compressing thin air before feeding it into the combustion chambers. This technological breakthrough, coupled with the aircraft's streamlined design, enabled sustained flight at altitudes where enemy fighters experienced dramatic performance degradation.
The crew compartment's pressurization system hummed quietly, maintaining an artificial atmosphere that allowed the 10-man crew to operate without bulky pressure suits. This comfort factor translated directly into mission effectiveness. Crews could remain alert and focused during lengthy flights that would have been impossible in unpressurized aircraft at such altitudes. As they approached the initial point for their bombing run, Captain Kellerman keyed his intercom to address the crew. The moment represented the culmination of America's most ambitious aviation project, executed at an altitude that redefined the very concept of strategic bombing. Below them, Japanese fighters climbed desperately toward an enemy they could see but never reach, their engines gasping in the thin air while the B-29s maintained formation with mechanical precision. The revolution in aerial warfare was complete. The age of high-altitude strategic bombing had begun, and the Japanese defenders were about to learn that their greatest challenge wasn't stopping the bombers, it was simply reaching them. Lieutenant Colonel Saburo Yamamoto gripped the control stick of his Kawasaki K-61 Heian as the aircraft shuddered violently at 26,000 feet. The engine, starved for oxygen in the thin atmosphere, coughed and sputtered like a dying animal. Through his frosted canopy, he could barely make out the silver shapes of American bombers still climbing above him, their contrails painting white streaks across the morning sky at an altitude that seemed to mock every principle of aerial combat he had learned.
The radio in his cockpit crackled with increasingly desperate reports from his squadron. Flight Sergeant Kenji Sato's voice, normally steady and confident, wavered with frustration as he reported his Nakajima K-44 Shoki losing power at 24,500 feet. Captain Yoshio Tanaka, flying the newer Mitsubishi J2M Raiden, managed to coax his fighter to 27,000 feet before his engine began missing badly enough to force him into a shallow dive. Yamamoto had been flying combat missions since the attack on Pearl Harbor 3 years earlier. He had faced American wildcards over the Coral Sea, tangled with P-38 Lightnings in the Solomon Islands, and survived encounters with the rugged P-47 Thunderbolts over the Philippines. Each engagement had taught him something about his enemy's capabilities and limitations. But this morning, staring up at bombers operating in airspace his fighters simply could not reach, he realized that the rules of engagement had fundamentally changed. The Kawasaki K-61, one of Japan's most advanced interceptors, had been designed for combat at altitudes up to 25,000 feet. Its liquid-cooled Kawasaki Ha-40 engine produced 1,175 horsepower at sea level, but that power dropped precipitously as atmospheric pressure decreased. At 26,000 feet, the engine struggled to generate enough thrust to maintain level flight, let alone climb higher or engage in combat maneuvers. Major General Minoru Genda, architect of the Pearl Harbor attack and now responsible for defending Japan's home islands, studied intelligence reports from the morning's encounters with growing concern. The photographs brought back by reconnaissance flights showed bomber formations maintaining perfect discipline at altitudes his meteorologists had initially dismissed as impossible for sustained operations. The implications were staggering. American bombers could now strike targets throughout the Japanese Empire while remaining virtually immune to interception. The engineering challenges faced by Japanese aircraft designers became apparent as technical teams analyzed captured American equipment and interrogated downed aircrew. The B-29's pressurized cabin system alone represented technology that Japanese industry had never attempted to mass produce. The complexity of maintaining atmospheric pressure while operating at extreme altitude required manufacturing precision and material science that stretched Japan's industrial capabilities to their limits. Flight Lieutenant Hiroshi Nishimura, recently transferred from the China theater to defend the homeland, experienced the futility firsthand during his first encounter with the high-flying bombers. His Nakajima K-84 Hayate, considered one of Japan's finest fighters, climbed steadily through 20,000 feet with power to spare. At 22,000 feet, the engine still pulled strongly. But as he passed 24,000 feet, the aircraft's performance began deteriorating noticeably. The cockpit grew bitterly cold as Nishimura climbed higher. Unlike the pressurized comfort of the B-29 crews, Japanese fighter pilots endured the full effects of high-altitude flight without environmental protection. Oxygen masks, when available, provided only basic life support. Frostbite became a constant threat as temperatures dropped to 40 degrees below zero. Physical discomfort translated directly into reduced combat effectiveness. At 25,500 feet, Nishimura's engine began running rough. The carburetor, designed for operations at lower altitudes, could not deliver the proper fuel-air mixture in the thin atmosphere. His airspeed indicator showed barely 180 miles per hour, far too slow for effective combat maneuvering. Above him, the B-29 formations maintained cruise speeds exceeding 300 miles per hour while operating in an atmospheric environment that reduced his fighter to a struggling, barely controllable machine. The Japanese Army Air Force's Technical Intelligence Division, led by Colonel Takeshi Morioka, worked frantically to develop countermeasures. Engineers studied every piece of information available about American high-altitude technology. Wind tunnel tests explored modifications to existing engines. Prototype turbocharger systems, reverse-engineered from captured American equipment, underwent rushed development programs.
Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The Mitsubishi Company's design team, headed by Chief Engineer Jiro Horikoshi, proposed radical modifications to the Zero fighter's engine installation. Turbocharging systems, similar to those used in the B-29, could theoretically extend the Zero's operational ceiling to 35,000 feet. However, implementing such modifications required months of development time and manufacturing resources that Japan's war-torn economy could barely provide. Captain Isamu Kashide, a test pilot at Nakajima's experimental facility, pushed prototype aircraft to their absolute limits in attempts to reach B-29 operating altitudes. His heavily modified Ki-44, equipped with an experimental turbocharger system, managed to reach 29,000 feet during test flights. But the modifications proved unreliable in combat conditions, with engine failures occurring regularly during high-altitude operations. The psychological impact on Japanese pilots proved as significant as the technical challenges. Flight Sergeant Toshio Yamada, a veteran of campaigns from Guadalcanal to the Philippines, described the helplessness of watching enemy bombers pass overhead beyond reach. The fundamental purpose of fighter aviation, intercepting enemy aircraft, became impossible when the enemy operated in unreachable airspace. Intelligence reports from captured B-29 crewmen revealed the extent of American technological superiority. The remote-controlled gun turrets, operated through sophisticated computing systems, provided defensive firepower without the weight penalty of multiple crew positions. The Norden bomb sight, capable of accuracy from extreme altitude, made possible precision attacks that Japanese forces had never experienced. The industrial implications became clear as Japanese engineers analyzed captured B-29 components. The precision manufacturing required for pressurization systems, turbocharger assemblies, and remote control mechanisms demanded machine tool accuracy that few Japanese factories could achieve. The aluminum alloys used in the aircraft's construction required metallurgical processes that Japan's resource-constrained industry could not replicate at scale. Wing Commander Tadashi Nakajima, coordinating fighter defenses around Tokyo, developed new tactics based on the harsh realities of altitude limitations. Instead of attempting impossible intercepts at maximum altitude, his squadrons would position themselves along probable flight paths at altitudes where Japanese fighters could operate effectively. The strategy required predicting bomber routes and timing intercepts for moments when the B-29s descended to bombing altitude. The weather became an unexpected ally in Japanese defensive planning. Cloud layers that obscured targets from high altitude sometimes forced American formations to descend into altitude ranges where interception became possible. Meteorological teams worked closely with fighter commands to predict conditions that might bring the high-flying bombers within reach. As autumn advanced and B-29 operations intensified, Japanese fighter pilots adapted to a new reality. The age of aerial superiority, where skilled pilots in maneuverable fighters could challenge any enemy aircraft, had ended. In its place emerged a technological war where engineering capabilities determined combat outcomes more decisively than pilot skill or tactical innovation. The silver bombers above represented not just a new weapon, but an entirely new form of warfare conducted from altitudes that redefined the very concept of air power. Dr. Edward Harrison wiped condensation from his thick glasses as he stood in the frigid test chamber at Wright Field, Ohio. The temperature had been dropped to -40 degrees Fahrenheit to simulate conditions at 30,000 feet. Inside the chamber, a mock-up of the B-29's pressurized crew compartment maintained a comfortable 72 degrees, while technicians monitored dozens of instruments, measuring seal integrity, airflow rates, and structural stress points. The pressurization system that made high-altitude B-29 operations possible had required solving engineering problems that no aircraft manufacturer had ever attempted. Harrison, Boeing's chief environmental systems engineer, had spent 3 years developing the technology that allowed 10 men to work comfortably in an artificial atmosphere while their aircraft flew through the stratosphere. The breakthrough had come during late-night sessions in Boeing's Seattle laboratories, where Harrison's team discovered that maintaining cabin pressure wasn't simply a matter of pumping in compressed air. The system required precise control of air temperature, humidity, and pressure differential while accounting for altitude changes, structural loads, and emergency decompression scenarios. Chief Test Pilot Edmund "Eddie" Allen had been the first to experience the revolutionary system during early B-29 prototype flights. Allen, a veteran aviator who had tested everything from racing planes to experimental bombers, described the sensation of climbing to 35,000 feet while remaining comfortable enough to drink coffee and write detailed notes about aircraft performance. The psychological impact on crew effectiveness was immediately apparent. Pilots and bombardiers could maintain peak concentration during lengthy high-altitude missions. The engine technology that powered the B-29's high-altitude performance represented an equally dramatic advancement in aviation engineering. Wright Aeronautical Corporation's R-3350 Cyclone engines incorporated turbocharging systems that maintained sea-level power output at altitudes where conventional engines produced less than half their rated horsepower. Master Sergeant Frank Rodriguez, a crew chief with the 500th Bombardment Group, understood the complexity of maintaining these technological marvels in combat conditions. Each R-3350 engine contained over 55,000 individual parts, from precision-machined turbocharger components to electronically controlled fuel injection systems. The maintenance requirements exceeded anything previously encountered in military aviation. Rodriguez's ground crew worked through Pacific heat and tropical storms to keep their assigned B-29s operationally ready. The turbocharging systems, while enabling high-altitude performance, proved temperamental in humid conditions. Intercooler ducts corroded rapidly in salt air. Wastegate actuators required constant adjustment to prevent overboosting that could destroy engines in minutes. The challenges of operating complex machinery at extreme altitude extended beyond engines and pressurization. Lieutenant Colonel Patricia "Pat" Sullivan, the Army Air Force's first female engineering officer assigned to combat operations, analyzed failure reports from B-29 missions to identify patterns that could improve reliability. Sullivan's data revealed that altitude created unexpected problems throughout the aircraft. Radio equipment designed for ground-level atmospheric pressure experienced frequency drift in the thin air above 25,000 feet. Navigation instruments gave erratic readings as temperature variations affected magnetic compass accuracy. Even ammunition for the defensive gun systems performed differently at high altitude, with reduced muzzle velocities affecting ballistic calculations. The remote-controlled gun turret system, one of the B-29's most advanced features, represented a revolution in defensive armament. Staff Sergeant Anthony "Tony" Marconi, a gunnery specialist at Lowry Field in Colorado, trained B-29 gunners on the General Electric computing sight system that made accurate defensive fire possible from high altitude. The system's complexity astounded even experienced gunners. Each turret contained motors, gear trains, ammunition feeds, and fire control computers that automatically calculated lead angles, range corrections, and ballistic adjustments.
The central fire control computer, weighing over 200 pounds, processed input from multiple sensors to coordinate defensive fire from 4 remotely operated turret positions. Marconi demonstrated how a single gunner could control multiple turrets simultaneously, switching between positions as threats developed from different directions. The system's sophistication allowed effective defensive fire at closing speeds and altitudes that would have made manual gun laying impossible. Enemy fighters approaching B-29 formations faced precisely aimed fire from guns that tracked targets automatically while compensating for aircraft movement and atmospheric conditions. The manufacturing challenges of producing B-29s in wartime quantities pushed American industry to unprecedented levels of precision and coordination. Boeing's production facilities in Wichita employed over 40,000 workers operating around the clock to meet delivery schedules that military planners considered essential to ending the Pacific War. Quality Control Inspector Margaret Maggie O'Sullivan examined pressurization system components with tolerances measured in thousandths of an inch. A single defective seal or improperly machined fitting could cause catastrophic decompression at altitude, killing the entire crew within minutes. The inspection process for each aircraft required over 800 individual checkpoints before military acceptance. The aluminum shortage created by wartime demands forced innovative approaches to B-29 construction. Engineers developed new alloys that provided necessary strength while using less critical materials. Magnesium components replaced aluminum in non-critical applications. Steel substitutions required redesigning structural assemblies to accommodate different thermal expansion rates at high altitude. Subcontractor coordination reached levels of complexity never before attempted in aircraft manufacturing. The B-29 program involved over 1,500 companies producing components ranging from specialized fasteners to complete wing assemblies. Bell Aircraft manufactured the Fuselage Center in Buffalo, New York. Martin built wing assemblies in Nebraska. Final assembly occurred at multiple Boeing facilities, where components manufactured across the country came together into complete aircraft. The electronic systems aboard each B-29 represented cutting-edge technology that pushed the boundaries of 1940s engineering capabilities. The aircraft's electrical system generated enough power to supply a small city, with multiple generators providing redundant power for critical systems. Radio equipment included frequency ranges that enabled communication across thousands of miles of Pacific Ocean. The radar systems installed in later B-29 variants provided navigation accuracy that revolutionized strategic bombing. The AN/APQ-13 radar set could identify targets through cloud cover from altitudes exceeding 30,000 feet. The system's complexity required specialized technicians who underwent months of training to understand vacuum tube circuits, antenna patterns, and signal processing techniques. Flight Engineer Technical Sergeant Carl Swade Johnson monitored these systems during combat missions, watching dozens of gauges and indicators that provided real-time data on aircraft performance at altitude. Engine parameters, cabin pressure, electrical loads, and fuel consumption all required constant attention during lengthy flights over enemy territory. The fuel systems alone represented an engineering marvel, with tanks containing over 5,000 gallons of aviation gasoline distributed throughout the aircraft structure. Fuel pumps maintained consistent flow rates despite altitude changes that affected fluid density. Transfer systems automatically balanced fuel loads to maintain proper center of gravity as fuel was consumed during flight. The B-29's high-altitude capability transformed strategic bombing from a tactical concept into a technological reality. The aircraft's ability to operate above the reach of enemy defenses while maintaining precision bombing accuracy represented the culmination of American engineering expertise applied to military necessity. The Silver bombers, cruising serenely at 30,000 feet, embodied the industrial might of a nation that had turned scientific knowledge into overwhelming military advantage.
General Curtis LeMay stood before the massive plotting board in his GARM headquarters, studying reconnaissance photographs that told a story no military strategist had ever witnessed before. The images, taken from B-29s flying at 32,000 feet, showed Japanese industrial targets with a clarity and detail that would have been impossible from lower altitude. Anti-aircraft gun positions, clearly visible in the photographs, pointed helplessly skyward at maximum elevation angles that fell thousands of feet short of the American bombers' operating altitude. The strategic implications of high-altitude immunity were reshaping the entire concept of air warfare. Major General Haywood Possum Hansell, LeMay's predecessor in the Marianas, had initially planned B-29 operations using traditional European theater tactics adapted for Pacific distances. But the aircraft's unique high-altitude capabilities demanded entirely new strategic approaches that maximized their technological advantages. Colonel Benjamin Benny, Chief of Targeting for the 21st Bomber Command, analyzed intelligence reports that revealed the psychological impact of unreachable bombers on Japanese civilian morale. Intercepted radio transmissions from Japanese home defense units described the helplessness felt by anti-aircraft crews who could only watch as formations of silver aircraft passed overhead beyond their weapons' effective range.
The Japanese had invested heavily in anti-aircraft defenses designed to counter raids at altitudes up to 25,000 feet. Their 88mm guns, equivalent to German flak weapons that had proven effective against European bomber formations, could theoretically reach 30,000 feet, but lacked the accuracy to engage targets at such extreme range. The time of flight for shells reaching maximum altitude exceeded 20 seconds, during which fast-moving B-29 formations could travel over a mile from their predicted position. Captain Dorothy Dot Reynolds, one of the few female intelligence analysts assigned to Pacific operations, compiled reports on Japanese industrial vulnerability that highlighted targets previously considered immune to air attack. Factories located in mountainous regions, protected by natural barriers and distance from probable bombing routes, suddenly became accessible to aircraft that could fly over geographic obstacles while maintaining bombing accuracy. The economic warfare potential of high-altitude strategic bombing exceeded anything military planners had previously contemplated. Japanese industry, concentrated in urban areas for efficiency and transportation access, presented target-rich environments that could be systematically destroyed by bombers operating beyond defensive reach. The psychological effect on workers who could see approaching bomber formations but knew their defenses were powerless to stop them contributed to declining production rates even before bombs fell. Lieutenant Commander Richard "Rick" Thompson, a naval intelligence officer attached to LeMay's staff, analyzed shipping reports that showed how high-altitude bombing affected Japanese maritime operations. Harbor installations, previously protected by coastal defense guns and fighter aircraft, became vulnerable to precision attacks from altitudes that neutralized both defensive systems. The B-29's ability to photograph targets during approach, conduct bombing runs, and document results during departure provided intelligence feedback that revolutionized strategic bombing effectiveness. Previous bombing campaigns relied on post-strike reconnaissance flights that risked additional aircraft and crews. The high-altitude B-29s could perform all functions during a single mission while remaining virtually immune to interception. Weather considerations, traditionally a limiting factor in strategic bombing operations, became less significant when aircraft could operate above most atmospheric disturbances. Colonel Martha Marty, the Army Air Force's senior meteorologist in the Pacific, discovered that B-29s flying at 30,000 feet could avoid weather systems that would ground conventional bombers operating at lower altitudes. The jet stream, a high-altitude wind phenomenon barely understood in 1944, initially created navigation challenges for B-29 crews, but ultimately provided tactical advantages once its patterns were mapped.
Missions planned to take advantage of jet stream winds could achieve ground speeds exceeding 400 miles per hour, reducing exposure time over defended targets while increasing fuel efficiency for the long flights across Pacific distances. Technical Sergeant George Hawk Hackens, a radar operator aboard the lead B-29 during the first high-altitude reconnaissance mission over Tokyo, witnessed firsthand how altitude affected target identification and bombing accuracy. The clarity of radar returns from 30,000 feet surpassed anything achieved at lower altitudes, where atmospheric interference and ground clutter degraded system performance. The intelligence gathered during high-altitude missions revealed vulnerabilities in Japanese air defense networks that had been invisible to previous reconnaissance efforts. Fighter bases positioned to intercept bombers at traditional operational altitudes were poorly situated to counter threats approaching at 30,000 feet. The geometry of interception, calculated for closing speeds and climb rates of conventional bombers, became meaningless when applied to aircraft operating in unreachable airspace. Production planning for Japanese industry, disrupted by the constant threat of precision bombing from unreachable altitudes, began showing signs of systematic breakdown. Factory managers, unable to predict when or where attacks might occur, struggled to maintain production schedules. The dispersion of manufacturing facilities, attempted as a countermeasure to strategic bombing, proved ineffective against aircraft that could strike any target within their operational range. The diplomatic implications of technological superiority became apparent as neutral nations observed American bombers operating with impunity over Japanese territory. Portuguese diplomats in Tokyo reported that Japanese officials privately acknowledged their inability to defend against high-altitude attacks. Swiss observers noted declining morale among Japanese military personnel who understood the hopelessness of their defensive situation. Major Sarah Sally Coleman, a logistics specialist at the Pentagon, calculated the strategic multiplication effect of high-altitude operations. Each B-29 mission required significantly fewer escort fighters compared to European theater operations, where bomber formations needed massive fighter protection to survive defensive interception. The resources saved on escort operations could be redirected to additional bomber production or alternative military objectives. The training requirements for high-altitude operations created new specializations within the Army Air Forces. Navigation at extreme altitude required different techniques and equipment compared to conventional bombing operations. Radio procedures adapted for thin atmosphere propagation characteristics. Oxygen system management became a critical crew skill that could determine mission success or failure.
The medical challenges of sustained high-altitude flight pushed aviation medicine into uncharted territory. Flight surgeon Major Doc Patterson studied the physiological effects of prolonged exposure to low atmospheric pressure even within pressurized aircraft. Crew endurance during missions exceeding 12 hours at altitude required new understanding of human performance limitations. The strategic bombing campaign enabled by B-29 high-altitude capabilities accelerated the Pacific War's conclusion in ways that traditional military planning had not anticipated. Japanese industrial capacity, systematically destroyed by unreachable bombers, could not be quickly rebuilt or relocated. The cumulative effect of sustained high-altitude attacks created cascading failures throughout Japan's war economy that conventional bombing at lower altitudes might have required years to achieve. The technological revolution represented by the B-29 stratospheric operations had fundamentally altered the balance of air power. Nations possessing high-altitude bombing capabilities could project force across vast distances while remaining immune to most defensive countermeasures. The Silver bombers cruising serenely at 30,000 feet had not merely gained altitude, they had ascended to a new realm of strategic dominance that redefined the very nature of aerial warfare. Colonel Jack Iron Mike Mitchell adjusted his headset as the formation of 12 B-29s maintained perfect alignment at 31,000 feet above the Japanese coastline. This was the 315th mission of the war for his aircraft, Victory Bell, and potentially one of the last. Intelligence reports suggested that Japan's capacity to continue fighting was rapidly approaching collapse, largely due to the systematic destruction delivered by high-altitude bombing campaigns that enemy forces could neither intercept nor prevent. The morning of August 14, 1945, found Japanese radar operators tracking the approaching formations with a mixture of professional duty and personal resignation. Chief Petty Officer Akira Yamashita, monitoring screens at the Choshi radar station, watched the familiar blips representing B-29s crossing into Japanese airspace at altitudes his remaining fighters could not reach. After months of helplessly observing these high-altitude intrusions, the radar operators had become unwilling witnesses to their nation's technological obsolescence. The cumulative effect of unreachable bombing had devastated Japan's ability to wage war. Major General Korochika Anami, Japan's war minister, reviewed damage assessments that painted a picture of industrial collapse accelerated by the immunity of high-altitude attackers. Aircraft factories, steel mills, oil refineries, and transportation networks had been systematically destroyed by bombers that operated beyond the reach of conventional defenses. Lieutenant Nancy Red O'Malley, a photo intelligence specialist aboard one of the trailing B-29s, documented the transformation of the Japanese landscape below through her high-resolution cameras. The clarity of images captured from 30,000 feet revealed the comprehensive nature of strategic bombing's impact. Where thriving industrial complexes had existed months earlier, only empty foundations and scattered debris remained. The final missions demonstrated how completely the B-29's high-altitude capability had revolutionized aerial warfare. Fighter pilot Flight Lieutenant Kenzo Watanabe, one of Japan's few remaining experienced interceptor pilots, made one last desperate attempt to reach the American formations. His Kawasaki K-100, among the most advanced fighters in Japanese service, climbed laboriously through 25,000 feet before engine power began failing in the thin atmosphere. Watanabe's experience epitomized the futility that had characterized Japanese air defense throughout the high-altitude bombing campaign. Despite months of modifications, experimental equipment, and tactical innovations, Japanese fighters remained bound by the physical limitations of their engines and airframes. The Americans had achieved something approaching aerial invincibility simply by operating in airspace that existing technology could not contest. The weather reconnaissance capabilities of high-altitude B-29s had provided an unexpected strategic advantage during the war's final weeks. Captain Helen Storm Patterson, a meteorological officer analyzing atmospheric data collected during bombing missions, discovered that flights at 30,000 feet could predict weather patterns with accuracy impossible from lower altitudes or ground-based observations. This meteorological intelligence proved crucial for timing the final strategic operations that hastened Japan's surrender. The ability to forecast clear weather windows for maximum bombing effectiveness, combined with immunity from interception, allowed American planners to coordinate attacks with unprecedented precision and reliability. The technological gap revealed by high-altitude operations extended beyond aviation into fundamental industrial capabilities. Japanese engineers, led by Dr. Ichiro Nakamura at Mitsubishi's research division, had spent the war's final year attempting to develop countermeasures to high-altitude bombing. Their efforts, while ingenious, highlighted the comprehensive nature of America's technological superiority. Nakamura's team had proposed everything from rocket-powered interceptors to stratospheric anti-aircraft missiles.
Prototype testing revealed that Japan's industrial base lacked the precision manufacturing, advanced materials, and electronic systems necessary to field effective high-altitude defensive weapons. The gap between conception and implementation proved insurmountable given wartime resource constraints. The human cost of technological obsolescence became apparent in the experiences of Japanese civilian populations who endured months of bombing attacks they could see approaching but were powerless to prevent. Air Raid Warden Taro Sakamoto, responsible for coordinating defenses in the Osaka Industrial District, described the psychological impact of watching silver formations pass overhead at altitudes that rendered all defensive preparations meaningless. The precision of high-altitude bombing had evolved throughout the campaign as crews gained experience with stratospheric operations. Bombardier Lieutenant Roger Ace Thompson, participating in his 53rd high-altitude mission, could place ordnance within yards of intended targets from 6 miles above the Earth's surface. The combination of advanced bomb sights, stable flight platforms, and immunity from defensive interference had created bombing accuracy that surpassed anything achieved in previous conflicts.
The final B-29 missions coincided with Japan's internal discussions about surrender, conversations influenced by the realization that continuing resistance against unreachable aerial attackers served no strategic purpose. Emperor Hirohito's surrender broadcast on August 15th acknowledged the enemy's possession of a new and most cruel bomb, but the systematic destruction delivered by conventional high-altitude bombing had already demonstrated Japan's inability to defend itself against American air power. Flight Engineer Master Sergeant Vincent Vinney, monitoring his instruments as Victory Bell turned toward home base after the final mission, reflected on how completely the war's character had been transformed by altitude. The Silver bombers had operated in a realm above the reach of enemy defenses, conducting systematic destruction with an impunity that redefined strategic warfare's possibilities. The post-war analysis of high-altitude bombing's effectiveness would influence military aviation development for decades. The B-29's demonstration that technological superiority could neutralize entire categories of enemy defensive systems established altitude as a primary factor in strategic aircraft design. Future bombers would seek even greater operating heights, while defensive systems would be redesigned to counter threats approaching from the stratosphere. Intelligence officer Colonel Patricia Pat Hamilton, compiling final mission reports at Tinian Air Base, calculated that high-altitude B-29 operations had achieved strategic objectives with loss rates significantly lower than any previous bombing campaign. The immunity provided by extreme altitude had protected American aircrew while enabling destruction that accelerated the war's conclusion. The maintenance crews who had kept the complex B-29 systems operational throughout the campaign represented another technological triumph. Chief Master Sergeant Leo Wrench Kowalski, supervising final aircraft inspections, took pride in maintaining machines that had operated reliably at altitudes where conventional aircraft could not function. The engineering achievement represented by sustained high-altitude operations had required not just advanced design but exceptional maintenance practices. As the last B-29 formations departed Japanese airspace on August 15th, they left behind a transformed understanding of aerial warfare's possibilities. The Silver aircraft that had cruised serenely at 30,000 feet had demonstrated that technological advancement could create military capabilities so superior that traditional defensive measures became obsolete. The Japanese pilots who had struggled futilely to reach the high-flying bombers had witnessed the emergence of a new form of warfare.
Lieutenant Colonel Yamamoto, grounded by fuel shortages during the war's final weeks, understood that future conflicts would be decided not by pilot skill or tactical innovation, but by the technological capabilities that determined which forces could operate in contested airspace. The high-altitude B-29 campaign had proven that supremacy in a single technological dimension, the ability to operate at unreachable altitude, could translate into overwhelming strategic advantage. The Silver Bombers had not merely flown higher than their opponents could follow, they had ascended to a realm of technological dominance that ended an empire's ability to wage war. Up next, you've got two more standout stories right on your screen. If this one hits the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.